Hello everyone. In today's video, we'll learn about the accelerated pure rolling. But before that, we'll discuss one problem I have given in my last lecture. The end, I have given one problem. That problem first we'll discuss. After that, we'll proceed to the pure rolling, which is accelerated pure rolling. So you can see in the screen that what was the problem. You can see, then you can take the reference, you can draw the diagram, then you can proceed with the discussion. Okay, I hope you have noted it down for the screen. So see, this is the problem. Problem is there is the outer ring, there is the inner ring, and between the outer ring and inner ring, some rollers are there which are rolling, and the outer ring is rotating with the angular velocity of omega, and this outer ring radius is 3r, and the inner ring, which is having 2r radius, that is rotating anti-clockwise with angular velocity of omega by 2. The outside ring, of course, is rotating with angular velocity of omega. There is a point P which is at distance r from the center and making angle 30 degree with the horizontal or the x-axis. So we have to find out what is the V center of mass and what is the condition for the pure rolling. So as it is a pure rolling, with respect to this ground, what should be the velocity of the center of mass? We know velocity of the center of mass should be omega into r, radius. But here what is the radius? 3r is the radius. So with respect to ground to the center, what is the distance? Distance is 3r. So omega into 3r, that should be the velocity of the center of mass. And the velocity of center of mass is in the direction of the x-axis. So 3r omega VCOM is 3r omega I cap. That is matching with the first option, option A. So option A is the correct one. Then we have to find out what is the velocity of the point P. Velocity of the point P. So velocity of the point P, if we have to find out, it is basically the velocity of the center of mass, or the velocity of the center, plus velocity of P with respect to the center of mass. What is the velocity of center of mass? As you know, 3r omega I, we have already found out, plus the velocity of point P with respect to the center of mass. See, with respect to the center of mass, this inner ring is rotating with omega by 2 angular velocity. So velocity of P with respect to the center of mass will be, let's say if I draw it here, 30 degree is the angle, velocity of point P. With respect to the center of mass, it is rotating. So this point is having the velocity of omega by 2 into r. Omega into r. So omega by 2 is the inner ring angular velocity. So the velocity of the point P will be in this direction. So this direction means this is 30, this is 30. So this becomes 60 degree. So we can write that this is having two components. One is negative x-axis and another is this axis. So this component is, x-axis component is omega by 2r cos 60. But what is the direction? Minus I. Another component of it is towards the z-axis. So this component is omega by 2r into sine 60 into k. So Vp with respect to the center of mass is the summation of these two. Omega by 2r cos 60 minus I plus omega r by 2 sine 60 k. So it is becoming 3r omega plus omega r by 4 minus I plus omega r by 2 into root 3 by 2, that is root 3 by 4 k. So this part is becoming 11 by 4 r omega I plus root 3 by 4 omega r k. So this is matching with the option B. So option A and B are correct options. Other options are not correct. So this part, if you have any doubt, you can understand from the concept of the combined motion that at any point the velocity is the velocity of that particular center plus with respect to the center what is the velocity. So that is the total velocity. And this point, as the inner ring is rotating with respect to the center with angular velocity of omega by 2 but is anti-clockwise, so of course at this point the tangential velocity will be perpendicular to the radius vector, but it is rotating in this direction, so it is tangential in this direction. So this is 30-degree angle, this is 30 degree, and this is 90 means this is 60 degree. So you can easily calculate. This is of course the magnitude is omega by 2 into r, and this you have to divide in two components. One is negative x-axis, another is positive z-axis. Then you will be able to find out what is the total velocity of point P, and this is the right answer. Now I will proceed to the accelerated pure rolling. Accelerated pure rolling means if some spherical object is gaining the speed or if it is losing the speed, that means it is having some acceleration or deceleration. Those kind of rolling motion which are in the condition of acceleration or deceleration, those kind of rolling motions are called accelerated pure rolling. If the velocity of the center of mass, we will write VCOM. Let's say initial velocity is 0. Let's say at t equal to 0, the velocity of the center of mass is 0. And then let's say the car is starting, so the wheel is starting to rotate. So it is gaining the speed. So VCOM is increasing with time. So that we can say that velocity of the center of mass for this spherical body is increasing with time. So we can say that it is having some acceleration. But it is not skidding on the road. So we can tell that it is doing the pure rolling on the road or on the ground. So what is the condition for that? So let's say at any point its velocity is VCOM, but this is of course variable. With time it is changing, it is not constant. And at that particular point the angular velocity is omega. Of course the radius of this spherical body is r. Then what is the condition for the pure rolling? VCOM should be equal to r into omega. And as I told that it is accelerated pure rolling, so V center of mass is changing with time. Maybe it is accelerating in the forward direction. So omega will also change with time. So omega will also be a variable quantity, omega t will write. So VCOM equal to r omega at that particular instant. At that instant. But it is changing with time. So if I do the differentiation with respect to time, what we will get? See, r for a particular spherical object is constant, so it will come out of the differentiation. So d omega dt. So this is A is the acceleration in the forward direction, let's say, and d omega dt is the rate of change of angular velocity, that is the angular acceleration r into alpha. So this is the condition for accelerated pure rolling. If there is no skidding or slipping happening at the point of contact, A should be equal to R alpha at every point of time if it wants to have the pure rolling. Or during the acceleration also, if it is not skidding, we can tell that A should be equal to R into alpha. So that means just we can imitate the same thing, we can draw the same diagram, but instead of that we can write ACOM, and it is also having alpha angular acceleration. So at this point, what is going to be the acceleration in the opposite direction. See, it is rotating or it is having angular acceleration, which is also giving rise to the tangential acceleration due to the change of omega. This is alpha into r in this direction. But the entire body is moving with acceleration of SCOM in the forward direction. So at this point, the point of contact of the body, it is having this acceleration ACOM in the forward direction and alpha r, that is the generated due to the angular acceleration in the backward direction. So this point of contact should not skid with respect to the ground, or point of contact should not have any acceleration in the direction of the motion with respect to the ground. So what is the condition? This ACOM should exactly balance this alpha into r. Then only the point of contact of the body will not skid with respect to the ground. So that is the condition for the pure rolling or accelerated pure rolling. Now, in accelerated pure rolling, friction plays a very important role. As this point, the point of contact of the body, it will of course try to slide over the ground, but it will not able to slide because friction will be acting there. The friction force is a very important force which will be helping the pure rolling to happen. The friction will adjust itself so that the point of contact of the spherical body will have the pure rolling condition satisfied. It will try to always adjust itself depending upon the force application point. It will try to adjust itself forward, backward. It will try to reduce itself. It will try to make itself zero sometimes. So friction will adjust itself. So friction or F adjusts. So how friction adjusts? Let's say this is a ring. Okay, let's say this is a disc. This is a disc having mass m, outer radius, let's say r. I am applying one force at any point, but here I am applying the force at the center. Let's say F amount of force I am applying at the center. What will be the value of friction and what is the direction of friction if it is pure rolling, if the disc is having the pure rolling motion? What is the value of F if disc is having pure rolling motion? See, one thing always remember, this force you are applying at the center of the mass is F. The disc is having mass of m. Then what is the acceleration in the forward direction for this force you are applying? F by m, of course. So as acceleration is there, what will happen? This will try to slide. The point of contact in the body will try to slide with respect to the ground. Now we got that acceleration in the forward direction, the linear acceleration in the forward direction, we are getting F by m. Now for the pure rolling or the rolling case, the body should also have some angular acceleration. But angular acceleration, see, with respect to the center, there is no torque acting. With respect to the center, there is no torque acting. Due to F is exactly passing through the center. So if the line of action of the force is passing through the center, there will be no torque generated due to that force. So what force will be there responsible for the rotation? So there should you should apply some force, or some force should be applied to make it rotate, to give it angular acceleration in order to counter A. Because you know, in order to have the pure rolling, A should be equal to alpha R. A is generated due to the force you are applying, but how alpha will be generated? So if the disc is moving with acceleration in the forward direction, this disc should rotate clockwise. But see, there is no clockwise torque is provided. If you do not apply any clockwise torque, how the body will get the clockwise angular acceleration? That time the friction comes. The friction will adjust itself in the backward direction of this particular disc. In this case. So see, with respect to the center, this friction is providing the clockwise torque to make it rotate with angular acceleration of alpha. What is the amount of that torque? Friction will be acting at the point of contact. If the direction is opposite direction, see, the clockwise torque it is getting provided due to the friction only. So what is the clockwise torque? F into R. And what is the angular acceleration? Torque by moment of inertia. This is angular acceleration. So what is the angular acceleration? Moment of inertia I. Now there is a chance that both will get balanced at some point of time, or there should be the value of some friction force so that it is having the pure rolling motion. Then we can calculate. So what is the value of I here? For the disc of mass m and radius r with respect to this axis, which is passing through the center and perpendicular to the plane, moment of inertia is mr square by 2. So we'll just write F into 2F mr. But you have to understand that acceleration will no longer be F by m, because some other force is also acting in the backward direction to reduce its acceleration. That is the friction force. So you have to find out the new value of A. What is the new value of A? What is the net force in the forward direction? F minus F by its mass, that is the acceleration or the linear acceleration in the forward direction. So that is becoming our new acceleration. Now in order to sustain the pure rolling motion, A should be equal to alpha into R. Now what is A? F minus F by m. That should be equal to alpha. Alpha is 2F by mr into R. So we are getting F minus F, m will get cancelled, R will get cancelled, 2 into F. So F is finally becoming F by 3. Now if you apply F force at the center of the disc having radius R, then friction will play a very important role in order to sustain the pure rolling motion. The friction direction, it will be in the backward direction, and the amount of force due to the friction is becoming F by 3 only. Now let's try to repeat the similar kind of scenario. Now let's say there is again I am giving disc of mass m and radius r. Now instead of applying the force at the center, I am applying the force at r by 2 distance from the center F. Now, what is the value of the friction force in order to sustain the pure rolling? Now last time or in the last problem I was giving the argument that due to the force it will get the acceleration in the forward direction. So what is the force that will give it torque necessary for the or torque required for the angular acceleration? That time we are telling that okay, friction will come and act in the backward direction. But right now see, force is also applied at such a point so that it gets applied in the forward direction and it is giving rise to the acceleration. At the same time it is also providing the clockwise torque in order to get the angular acceleration. Then what will be the direction of the friction and will the friction act or not? That is a point of concern. Now at this point where I do not know whether the friction will act or which direction it will act or not, I just take any random direction of friction. Let's say I will take friction direction. Let's say I will take backward only. Friction is acting. We'll assume if the friction value comes negative, then we'll think that okay, whatever direction we have assumed, that direction is wrong. The direction will be in the opposite direction if the friction value comes negative. But right now let's assume that friction is acting in the backward direction. So what is the acceleration of this particular body? F is acting in the forward direction, friction is acting in the backward direction, so net force in the forward direction is becoming F minus F by m is the acceleration. That is our first equation right now. Secondly, this is the acceleration part gone. Now, in order to have the pure rolling motion, it should also rotate. So, it should have some amount of torque that is applied in the clockwise direction. So, clockwise direction C with respect to the center, due to the capital F, or that is the external force, due to that it is also getting one torque. That amount is F into R by 2. So capital F into R by 2 amount of torque is getting applied in the forward direction due to the applied force only. And due to friction, as we assume that friction is acting in the backward direction, friction is also providing the clockwise torque with respect to the center. The amount of torque is F into R. So we'll write F into R. That is the net clockwise torque that by I, that is moment of inertia, that is mr square by 2, that is going to be our angular acceleration. So we can simplify this part and we can write F plus 2F by m into R, that is our value of the acceleration. Now in order to have the pure rolling motion, in the case of accelerated pure rolling, this should satisfy. A should be equal to alpha into R. Now we'll just put the value of m. Alpha is F plus 2F by m R into R. We are getting F minus F is getting equal to F plus 2F. So see, 3F we are getting 0. So value of F we are getting 0. So see, we are getting the value of friction to be 0. So there is no friction is getting applied if I apply F amount of force at R by 2 distance from the center in the upward. So friction will adjust itself to 0 in this case in order to support the pure rolling or the accelerated pure rolling. Friction will be 0. Now why it is coming? How to understand at which point if I apply force the friction will ultimately come to 0, then it will change its direction. You saw that if we apply F force at the center, the friction was acting in the opposite direction, the backward direction or the direction of the motion. If we apply F force, let's say at some distance down from the center, of course that time also friction will act in the backward direction, because due to this F force, capital F force or the external force, this will of course get one acceleration in the forward direction, but it is providing the anti-clockwise torque, but it needs to rotate in the clockwise direction. So friction must supply this amount of that required amount of torque in order to sustain the pure rolling motion. So friction will act in the opposite direction. So this is simple, that from here at the point till the point of contact, if we apply the force from center, the F force, if you apply the F force to this body, it will of course requires the friction force to be acting in the backward direction in order to sustain the pure rolling. But there will be some difference if I apply the F amount of force at some height above the center. If I apply F force here, let's say, we'll discuss this and then we'll come to the actual conclusion. At what point, if we cross, that then the friction will change its direction. So see, we got to know that at r/2 distance, in the last example, at r/2 distance, if I apply the F amount of force, friction is coming to 0. So right now I am applying the F force at the topmost point of this disc. Again, disc having mass m, radius r. Let us assume, this time also let us assume that friction is acting in the backward direction. Then what is acceleration? Total force in the forward direction is F minus F by m. That is the net acceleration in the forward direction. That is the equation 1. And due to capital F force, clockwise torque that is provided to have the angular acceleration, as well as due to this friction also, it is having total clockwise torque plus F into r. By the moment of inertia, that is going to be our angular acceleration, and that is 2F plus 2 small f by m into r, that is alpha. So alpha r is actually becoming 2F plus 2F by m, and in order to have the pure rolling motion, A should be equal to alpha into r. So we will be able to find out what is the value of the friction force, or what is the direction of the friction force. If friction force comes negative, then whatever direction we have assumed, that is not correct. We have to reverse our direction. So see, we are getting that m will get cancelled. 3f equal to minus f. So f we are getting equal to minus f by 3. So that means friction is coming negative. That means whatever direction we have assumed, it is wrong. We have to just change the direction in the forward direction. So friction will act. So see, this time if you apply F force at the topmost point, this friction is basically trying to increase the acceleration, because it is acting in the direction of the motion. It is trying to increase the acceleration and it is trying to decrease the angular acceleration. In the first case, when F was getting applied at the center, then friction was acting in the opposite direction. So that time, what was the role of frictional force? Friction force was trying to deaccelerate the body, but it was trying to increase the angular acceleration. It was trying to decrease the linear acceleration and it was trying to increase the angular acceleration. But here in this case, friction is trying to increase the linear acceleration and it is creating one anti-clockwise torque so that this body decreases its angular acceleration. So friction plays a very important role. It adjusts itself so that the body does the pure rolling. It also adjusts itself in the terms of the value, in the terms of the direction also it adjusts itself. And sometimes it completely becomes zero. Now I was talking about at what point if we apply the force, the friction will become zero. What was the point if you apply the force? In order to make the friction completely sacrifice itself, for its pure love, that is pure rolling. So friction, at some point, if you apply the force, friction will completely sacrifice itself for its love, that is i.e. pure rolling. So there will of course be certain point, if you apply the force, the friction will be zero. Let's say that distance is x from the center. For the disk we have already found out. For disk we have already found out that x equal to r by 2. In the last example, we have found out that when the force was getting applied at r by 2 distance above the center, the friction was coming 0. So now let's say any spherical body, let it be a ring or a sphere or a hollow sphere. Let's say for a spherical body, the moment of inertia is I. Now friction will make 0. There is no friction acting. That means, so this force itself is providing it the value of the linear acceleration in the forward direction, as well as it is providing the enough torque in the clockwise direction in order to sustain the pure rolling. Then what is the acceleration? F by m. Because friction is 0, it sacrificed itself. What is the torque? Net torque applied? F into x, that is clockwise direction. So due to that, the alpha is getting generated by I. Torque by moment of inertia is the angular acceleration. Now in order to have the pure rolling, alpha into r should be equal to a. So we'll just put f into x into r by I, that is equal to f by m. So we are getting the value of x, f will get cancelled, I by m into r. So this is a very important point, that if I apply my force above the center at I by mr distance, the friction will adjust itself and it will ultimately become 0. So in the case of disk, what is this value? I by mr, that we have already discussed. Right now let us understand this by the theorem. Mr, that is r by 2. For the ring, I by mr is how much? Ring, it is mr square by mr, that is r. That means if you apply your force for the ring at the top point, that time the friction will be 0. For sphere also you can find out. For sphere, value of I is 2 by 5 mr square by mr, that is 2 by 5 r. At that point above the center, if you apply the force, the friction force will become 0. So the value is I by mr. That distance, if it is above that distance, then the friction will be acting in the forward direction. If it is below the distance from the point of contact, then the friction will be acting in the backward direction, and it will ultimately try to increase the angular acceleration and reduce the tangential acceleration and reduce the linear acceleration. So this is a belt pulley arrangement. This is a cylinder around which one wire is wrapped, and that is ultimately supporting this mass M hanging. Now the system is kept at rest, and after this point at t equal to 0 the system is at rest, and then it is left from the rest. Then it will ultimately, this mass will move down with acceleration A. So you have to find out what is going to be the acceleration if this cylinder is having the pure rolling motion. That is the condition. The cylinder of mass M and radius R is having the pure rolling motion. Then what is going to be the acceleration of this mass M? We will solve this problem. But before that, just a small theory is required. It is very similar to the velocity concept, but we'll see it. That what is the condition for the pure rolling in kind of accelerated pure rolling? If the linear acceleration is A and angular acceleration is alpha, then at this point the relative acceleration with respect to the ground in the direction of the motion should be 0. So due to this, linear acceleration is getting forward direction acceleration of A, but due to this rotation it is getting in the backward direction alpha into r. So ultimately it is becoming 0 at this point of contact. So A is equal to alpha into r. So net acceleration at the bottommost point, at the point of contact in the body, that is having acceleration in the forward direction, that is equal to 0. A equal to 0. Total acceleration. Total acceleration for the topmost point, of course due to the linear motion, it is having a acceleration or linear acceleration in the forward direction. But due to the rotation also, it is getting one acceleration in the forward direction, that is alpha into r. So total angular acceleration or total acceleration for the topmost point is A plus alpha into r, that those are acting in the forward direction. That amount is 2 into A. For the center is exactly moving with the acceleration of A. So we can tell that from the point of contact to the topmost point, the acceleration is increasing from 0 to A to 2A. If we draw the vector diagram, we'll see that the acceleration is A, this is becoming 2 into A, topmost point. So that same concept will require here. If this mass is moving down with acceleration of A, what is going to be the acceleration for this cylinder in the forward direction? Because it is wrapped around this cylinder. But see, acceleration of this string is A, because it is also moving down with A. So for the center, what is going to be the acceleration? Half of it. So it is A by 2. And one more thing, tension for this body of mass small m, upward direction is acting. Tension is acting for this cylinder like this. So it is a very similar to the force applied at the topmost point for the pure rolling case. So here in this, instead of capital F, we are applying tension here, and that tension is generated due to this mass. So we'll just draw the free body diagram for this body. Of course, friction, we saw that it is acting in the forward direction, let's say T. Center, it is moving with A by 2. It is also having one angular acceleration. So if I draw the free body diagram, this is the free body diagram. For this mass, what is the free body diagram? Tension is acting upward, weight is acting downward, and it is ultimately moving down with acceleration A. So we can write mg minus T is equal to m into A. That is our first equation. Second equation is for this body. We will write that T plus F is becoming capital M into A by 2, which is moving with acceleration A by 2 in the forward direction. That is our second equation. Another equation will come, that is the torque. So T into R, that is the forward, or that is the clockwise moment or clockwise torque minus the anti-clockwise torque, that is going to be our I into alpha. But here, what is the value of alpha? It is having pure rolling motion, but the acceleration here is A by 2. So we call that alpha into R, that is equal to A by 2. So what is the value of alpha? Alpha is A by 2R. We'll just put that A by 2R. That is going to be a third equation. We solved all these things. So T minus F is, we are getting M by 4. So if we add these two equations, we'll get that. Second and third equation if we add, we'll get 2T is MA by 2 plus MA by 4, that is MA by 2 plus MA by 4. We are ultimately getting 4 3MA by 4, 2T. So T value we are getting 3M into A by 8. Now this first equation will focus. We'll just put the value of T, we'll get the acceleration. So mg minus 3m into A by 8 is equal to m into A. So ultimately this will go to that side. We'll get the value of acceleration is 8 mg by 8 small m plus 3 capital M. That is going to be the acceleration for the block small m downward. I hope it is understood. So one last thing I want to discuss along with you guys, that is pure rolling motion on inclined plane. So I am not going to solve any problem, I am just giving you the brief idea. Let's say the angle of inclination for the inclined plane is theta, and there is one cylinder of mass m and radius r. If I leave it from here, it will roll and reach the bottom. Let's say it is rolling completely. It is not slipping or something, it is rolling completely over the inclined plane. What is going to be the friction force direction in the case of this cylinder? This is this cylinder. It doesn't matter whether it is cylinder or sphere, but for the cylinder, let's take the example of cylinder only. If its mass is capital M, the net downward force acting along the incline, that is mg sin theta. And of course mg cos theta is acting, but it is not required because due to this mg sin theta component of the force only, it is moving downward with some acceleration, let's say. Then what will be the direction of the friction force? So this, if you rotate and put it here, you will see that one constant force amount, that is mg sin theta, is applied at the center of the cylinder. You have seen in the example we have talked that if some force is applied at the center for the cylinder, this is not providing any torque for the cylinder to rotate in the forward direction. So who will supply the torque? The friction will supply the torque. This is only providing the linear acceleration down the inclined plane, but friction will come as a masiha, and it will ultimately try to reduce the linear acceleration in the forward direction and it will try to increase the angular acceleration in the clockwise direction so that it helps the body to rotate purely. So the friction force will be acting in the opposite direction. Now it is rolling down. So this is the case of rolling down. Now let's say I have thrown one sphere, or let's say I have thrown one cylinder up the inclined plane. What is going to be the direction of the friction force? Same, M mass, R radius, cylinder, I have thrown it up the inclined plane. Angular inclination is theta. Let's say it is deaccelerating upward. It is deaccelerating upward. Who is providing the deacceleration? Of course, the downward component of the weight is providing it the deacceleration. Then while it is deaccelerating upward, is it increasing its angular acceleration? No, because if it increases angular acceleration while it is deaccelerating forward, it will ultimately slip over this surface. In order to have the pure rolling motion, friction will come also again here. Friction will try to provide the anti-clockwise torque, because see, in this direction it has to, or it needs to deaccelerate angularly. So the angular deacceleration will be in this direction. Angular deacceleration in this direction means angular acceleration in the opposite direction. So in this case also it is having angular deacceleration rotating upward, but that means the angular acceleration in the opposite direction. So who will provide the necessary angular deacceleration it needs to have in order to sustain the pure rolling motion? Of course, there is friction. The friction will act in the upward direction. Okay. So friction here will try to reduce the linear acceleration, of course. At the same time, it will try to reduce the angular acceleration also, or it will try to provide the necessary angular deacceleration required to sustain the pure rolling motion over the inclined plane. I hope this part is clear. Thank you for watching.
Now you can try to attempt this problem. This problem was given in JEE Advanced 2022 paper 1. So in this problem, one sphere is kept on an inclined plane. So the downward force mg sin theta is of course acting on this sphere, but instead of giving it any force, one anticlockwise torque is provided.